Yo, we love that. She's actually not.
Survey that we have. It's about your first year and your interest in projects in your first year. So you can scan the QR code or go on your phone and fill out the survey. So yeah, we do that as you come in.
We have a brief survey that we'd like you to fill out from now until the beginning of lecture
This is to gauge your interest in our first year curriculum and how your first year has been going and what courses you like and you don't like, and also to gauge more interest in project-based courses like EG1003. The survey is totally voluntary, but if you do have any questions, feel free to ask Professor Braingardner and raise your hand.
first year experience. A couple of quick updates before we get into the lecture today. Milestone 3 is next week. Your midterm grades will be posted soon, so be on the lookout for those. There is a mid-semester project survey, which is a chance for you to let us know if you're having teamwork issues with the project. That's been posted as an announcement to the website, so please fill it out by Sunday. Remember, next week is the last lecture, so we're the second to last lecture, after which the lecture period will be available for you to work on your projects. Recitation in the lab will continue, but there are only 10 lectures for EG1003. And then remember that the RAD competition will take place in the last week of class. For the RAD teams who are interested in entering, there will be a practice in the makerspace Tuesday, 12:30 to 2, and then an actual run in Thursday, 12:30 to 2 here in Pfizer. So today I want to make sure everybody's quiet during the lecture. Make sure you're paying attention, as well as providing respect to our guest lecturer. Today we have Professor Kapila from the Mechanical Engineering Department. He also runs the
Can you guys hear me? Okay, let's get started. So I'm going to be talking about research at the convergence of frontier technologies. Convergence research has become quite in thing these days. And you will see what are the frontier technologies that we are going to be looking at. So very quickly some outline. I'll tell you a little bit about hands-on mechatronics and robotics education. How and why we do it, primarily because of the workforce of the emerging future. Then I'll describe a little bit of my mechatronics and robotics research over the last 20 plus years. But in the last 3 years, we have moved on to convergence research, so I'll talk about that and quickly acknowledge various organizations and people. So, what's happening with the engineering and technology workforce for which you have come here to get your undergraduate degree? New York City, maybe 10, 12 years ago, was primarily just running on the financial businesses and maybe a little bit entertainment. But today, New York City economy is driven to a large extent by a lot of the innovation and startup culture. And these innovation and startup economy companies require engineers and developers who can collaborate with one another and on a lifelong basis learn from one another. Okay? Just a 4-year college degree ain't going to do it. You also have to be able to work with people from very different backgrounds, not just mechanical versus electrical engineering, but also business people, law, medicine, so on and so forth. So at the bare minimum, we require our engineering students to have a highly interdisciplinary education. Multidisciplinary is not enough, interdisciplinary. You also need to have significant practical experience through hands-on projects, and you have started to have that through our makerspace, for example. At the same time, I think all students should have a broader experience in education because 20, 30, 40 years ago, people could graduate from college and get a job with a multinational company and be set for life working there for 30 or 40 years, right? Today, I think entrepreneurial experiences are pretty critical so that maybe instead of getting a job, you could go and create jobs for 20 or 30 other people. At the same time, there are some emerging trends. In the old days, people would specialize in a very narrow focus area, and that might still work for some people, but by and large, people need to learn a number of different areas, be a journalist in your field. Also, in old days, people could sit on their desk, continue to work from 9 to 5 without talking to anybody else. That ain't going to happen today. Instead, we're going to be working in small teams and these teams will continuously reconfigure depending on how the projects are changing or progressing. So then why mechatronics and robotics? I believe mechatronics and robotics both are still very nascent and developing fields, which means that if you can make some contributions in this area, you can create long-lasting businesses and entrepreneurial ventures. Mechatronics and robotics, by their very nature, require you to work hands-on. Okay? It's not enough to learn some theory and do some simulations, but rather you are going to have to create whatever it is that you have in your mind as a physical artifact. Okay? So it allows you to do hands-on learning. You could also do a lot of research and engage in creative aspects. So by going to mechatronics and robotics like curriculum, we are trying to modernize also our curriculum. We have done that already at the graduate level, where we have a master's in mechatronics and robotics program. Hopefully soon enough we'll have an undergraduate minor in robotics. And then if you also look at the trends in the business and technology, Internet of Things, quantified self, wearable technology, self-driving cars, smart homes, delivery drones, companies like Google, Uber, Amazon, GE, they are all engaged with mechatronics and robotics in one or other aspect. Many of these images that you will see on the site sometimes will be projects that students have done in the lab. So this is actually our Masters in Mechatronics and Robotics program that you might want to look at online if you decide to go on after your bachelor's to the graduate degree. It's received a lot of publicity in media, and we have held a number of workshops for this program. We also have created an ecosystem with partnering with industry to provide a lot of real-world example projects for students to work on. And here are some of those projects that students have worked on, and they've gone on to get jobs in several of the companies that have funded these projects. So now when we move on from that little educational pitch to more on research, so last maybe 10, 12 years I've focused a lot on mobile mixed reality human-robot interaction. This happened after the first time I came across somebody using an iPhone that looked to me like a very powerful device, but at the same time they were doing certain other things with clunky interfaces, and the thought popped up in my mind why we could not use the same iPhone for doing many of these other kinds of things as well. So essentially what we are going to talk about is a couple of different ways in which you can use these smart devices to interact with physical world. In one case, the device could be embedded on the physical test bed to do the sensing, to do the communication, to do the computing, or in the other case, device could be held by the human operator in his or her own hands while interacting with this hardware. What we need to do is make use of things like 3D graphics to create highly intuitive augmented reality frameworks, perform some estimation and control algorithms, make use of computer vision to be able to identify objects and areas in the object of interest, and then also some highly compelling and interactive user interfaces. So we have taken our undergraduate control lab, done a lot of experiments of that control lab using these handheld devices and embedded devices, essentially iPhones and Google Android phones, and we published a bunch of work on that, on things like controlling DC motors, doing liquid level control, flying helicopter test beds, so on and so forth. So let me show you one example through this video. Inverted pendulum is a pretty common experimental test bed in feedback control education. The idea is that if I give you a pendulum and ask you to balance on your hand, what do you have to do? If you put a pencil or a pen, and I ask you to balance on your hand, anytime the pencil is falling to the left, you move your hand to the left so that the center of gravity falls on your hand. If the pencil is falling right, you move your hand to the right. So you're making use of your eyes as a sensor, and then you're making use of your brain as a control algorithm to decide which way to move your hand, and then you use your muscles to apply that control action, right? In a similar way, a typical inverted pendulum control system has sensors embedded on the platform. These could be potentiometers, encoders, tachometers, so on and so forth, to monitor the pendulum angle and to monitor the position of the card, which is replacing the hand here. But what we did with this test bed is we said we are not going to use any of the embedded sensors on the pendulum test bed. Instead, we 3D printed a mount and mounted it on the test bed to hold a smartphone into it. Okay? And then we put in this marker platform in front of the inverted pendulum with a few different markers on it to figure out if those markers are in the perfect vertical plane as viewed by the cell phone camera, or if they are tilted to the left or right, and whether they are in the smack center of the screen or left or right offset from it, so that we could use that information from computer vision algorithm to do the feedback control. So let's let the video play. So that's the marker platform. The student is putting the smartphone on the test bed. Now you see those markers, and the pendulum is straight and up, not falling down, right? So those smartphones have a lot of capability. You don't use them just for social media or reading news or playing games. So in the same manner, here is a DC motor test, but that actually, if students want, they can take them home with them. We haven't made enough copies, or you can print one on your own. A typical DC motor test bed like this, if we buy it from the manufacturers, might cost us about $5,000 or $6,000. Okay. Instead, one could make a device like that using 3D printing in the makerspace, buying some off-the-shelf motors, Arduino microcontrollers, and power supplies for less than $300, maybe even $200. Okay. And then the sensors and control are all done using the smartphone. In the first case, the smartphone is mounted on the test bed. In the second case, we have a couple of markers on top of the test bed, as well as on the DC motor arm, which we want to control as if that's a robot. But then we use the smartphone to get those marker coordinates to do the control. So here's a quick experimental video. So this is all using Arduinos, motor control boards, power supplies, using just lithium-ion batteries. He's putting it in the cabinet there underneath the motor. So now he's holding the iPad in his hand to command the motor. That purple link is the augmented reality link. You move that by your hand, and underneath the real link will move accordingly. On the left panel, we can do some control design, or on that same interface. We have used this for doing a lot of educational studies with the students who take the lab, and we have shown that making use of augmented reality in doing teaching and learning in this manner is much more effective than the traditional approach. Here is an example of commanding and controlling a mobile robot using an iPad app. So the idea here is that we have an obstacle course in which there is a mobile robot sitting, and up on top there is a camera looking down on the obstacle course. The camera will find where the robot is in the scene by making use of some markers that are placed on the robot, and then it will simply send the robot's pose and location to an iPad app, and in that iPad app we will interact through touch interactions to command the robot. So for example, we might be able to draw the path that we want the robot to take. We might be able to simply tap on the screen to tell where we want the robot to go, and then the path will be automatically generated. So right now he's drawing the path just by sketching on the screen, right? So a highly intuitive and natural way of interacting with robots without having to train the shop floor operators as to how to work with robots. If you throw in some obstacles after the path has been drawn, we have algorithms that can automatically make the correction to the robot's path. We also use the same techniques to work with activities related to healthcare. So later on you will see some examples for stroke rehabilitation. On the top right is a robot with an iPad app where you can see a physically disabled toddler who cannot explore his or her environment. But now that they are sitting on this robot with the iPad right in front of them looking at the environment, by touch interaction with the iPad, they can drive the robot to wherever they need to be in the environment, allowing a physically disabled toddler to explore his or her own environment in that manner allows them to undergo their proper cognitive development. Similarly, for dental training, we have created a mechatronic dental trainer. Most of the dentists, when they are going through their education, they don't really undergo any practical training in this matter. So the first time they may be extracting a tooth is when you go and have them do an extraction for you. That's not necessarily very good. So in this device, what we have is these tooth models embedded with some sensors and then an extractor that also has sensors embedded on it. And a typical person, when you ask them to extract the tooth, what they do is pull, just a straight pull, okay? Which is not very good because the tooth may still not be loose. But by 10th or 12th trial, they start to make sideways and up and down motion to loosen the tooth before they make the final extraction. So with a training like that, they could do much better. Here is a device in the back, this robot that we call Nurse Judy, that makes use of Alexa-like voice commands as well as computer vision to allow the surgeon to ask for various tools during surgery. Okay, so now let's move on to from mechatronics and robotics to convergence research. Okay, what are these frontier and disruptive technologies? What is causing the disruption? What is the driver for this disruption? And what kind of research at the convergence of these technologies is happening in our lab? I don't know how many of you have heard about hardbotics. Hardbotics, there was an article about it in Washington Post last year, maybe in March or April. And then by September, they had hired one of our students. Hardbotics is a robot staffing company. Okay? Like 30 years ago, if somebody needed an admin in their office, they would call up this human staffing company, and the staffing company will send you a person to do the work. If on your manufacturing shop floor you need a robot to do certain operations, but you don't want to spend $80,000 buying the robot, doing all of the integration by yourself, or paying somebody to do that, you call Hardbotics. They will come in, study your problem, create a solution, deploy the robot, and now you owe them $20 per hour for a minimum number of hours and a minimum number of years. So basically, robot as an employee on the shop floor. Okay. AI on the top right, I put that image there because, believe it or not, there's a robot in there with the cap on its head. That's from our lab. Caesar disappeared, I think, in Daily Show a few years ago. And this show was talking about how AI and law are intersecting, where who gets parole or who gets mortgage, and all of that is being made, all those decisions are being made through computer algorithms. Virtual App is a company in Dumbo, just maybe a mile from here. They also had one of our students a few years ago. They are making use of mobile robots along with 360 vision and augmented and virtual reality to market high-end commercial and residential real estate. And you can use those same technologies to also create new ways of doing online retail. Blockchain, many of you might have heard of blockchain and you might think that, well, that's what we use for cryptocurrency, but actually blockchain can be used for a lot of activities in the physical world also. This is an image from a New York Times article when a law professor started to teach a blockchain course at NYU. The course was filled up within almost no time. But we will use this for robotics as well. So what are the drivers for the disruption through these frontier technologies? Even 10 years ago, if you wanted to build a robot, you needed to be in a lab that was probably funded to millions of dollars, right? Robotic hardware, the motors, the sensors, the microcontrollers, the embedded control, all of those things used to cost a lot. Today, many of those individual pieces of hardware are available as open source, low-cost things that you can just go online, get the design, walk into the maker space, start printing stuff on your own. A lot of people even put their robot designs as shared files on GitHub, for example. Also, a lot of the computational resources that we used to use 10, 15 years ago would cost us tens of thousands of dollars to program these robots. Okay? Today, you can get ROS, Robot Operating System, free of cost online. You can get OpenCV for computer vision free of cost online, right? So open source hardware and software, freely available computing tools, and then the third thing is, you guys are here to get your undergraduate education. Maybe you take robotics, maybe you don't take robotics, right? But what if 5, 7 years down the road, you need to be able to do something in robotics? Well, there's a lot of online stuff that is available, MOOCs, and all these places. There's a lot of stuff that you can get online if you have the patience and discipline to learn on your own. Okay? So open source hardware, and democratization of access to knowledge, that is all driving disruption. You could go into your basement for a few $1,000s and start building robots that could really make a difference. Okay? So in our lab, we make use of not just robots, but how we might be able to bring together augmented and virtual reality with robotics. Or how we might be able to make use of AI or machine learning along with robotics. Or what might we be able to do by integrating blockchain with robotics. So that's the convergence aspect. Bringing multiple ones of these disciplines together to create something innovative. Okay, so first I'm going to talk about augmented reality for human-robot interaction. Okay, so the idea is we want to design, develop, and test novel mobile-based augmented reality interfaces so that users can intuitively and naturally interact with the robots without requiring any extensive training. Okay? So the augmented reality essentially becomes a translational mechanism, if you will, between the human and the robot to pass on the intent and the environmental information. Okay? So human is going to inform the robot what needs to be done that is needed so that robot can perform the task and also to know its end effector location. And then the robot would be informing the human. And then human would also provide the boundary of the robot to the augmented reality. So the motivation is there is a lot of potential for HRI using augmented reality to make it highly natural and intuitive. We need friendly user interfaces so that technicians don't have to go through extensive training to work with these robots. But even beyond that, if we want robots to be pervasive and appear in our homes and workplaces, then we have to allow these robots to work in unconstrained environments. Today, robots, when they work in shop floors and manufacturing environments, those are pretty controlled environments. Our homes are not controlled environments, right? So, as a first step, what we are doing is making use of a number of these visual markers to create the workspace around a robot, identify where the robot is, and identify objects that with which the human wants to interact. So we're going to have a robot arm. Actually, it's going to have two arms, this robot, a left and a right arm. There's going to be a bunch of markers placed in the environment, and then the human will be able to go around with the tablet to capture that environment on the tablet screen, make it interactive, and start moving objects, for example. Okay. And the objects that we want to interact with will also have markers on them. At any given time, we need to have at least 4 markers in the scene so that we can create the homography for the plane to be able to interact with these objects. Right? No training, no programming, no nothing. You simply bring in the tablet, start interacting with the object. If the object is now hidden behind the robot arm, you just move back wherever the object is. It doesn't matter. You don't need to be standing still or static. You're moving around as you interact with these objects. But you might say that, well, you just told us that you want to have an unconstrained environment and you don't want to have too many things in there. You put in all these visual markers. I'm not going to put that in my home all over the place, right? Yes, we'll address that problem momentarily. So here we move on from a single manipulator robot to a bunch of mobile robots that are going to be in the environment, no sensors on the robot or in the environment, except for the single iPad that the user will bring in to now start moving around objects in the environment through those mobile robots. So we have all these mobile robots. We have objects that have the markers, and the user touches on the screen and moves those objects in the screen from point A to point B, and the real robots are going and doing your bidding there, right? We need at least one robot at any given time to be stationary so that I can fix a coordinate frame on that, and instead of now having other visual markers fixed in the environment, what we do is make use of actually iPad's built-in inertial measurement unit to figure out the remaining information to get the coordinates next. Okay. So those 2 examples, they were using markers distributed all over the place to do the control. Now what we are going to do is we will have only a single marker in the scene. It's always permissible that somewhere in the scene we might be able to put a single marker. Then beyond that, we will make use of markerless approaches to capture the scene. This comes from the Google's AR app. Okay? So the idea is we will use the markerless approach along with the marker approach to find out planes where the one marker is placed, identify the objects so that we can start interacting with those objects. So the idea is I have this little robot. There is a single marker placed near the robot. We know where that marker is relative to the robot. Beyond that, there is a bunch of objects lying in front of the robot. We will bring in the Google Android near the robot. The user will use that Google Android phone to tell where the marker is on the screen. After that, the user is moving around in the environment, doesn't matter. Then user will just click wherever the objects are seen on the screen and then dictate where to put them out. Okay? The user can do that for individual objects, or the user can also sequence, I want to move these 3 objects from their original location to some goal location. Let's look at the quick video. So the center cursor is brought in. That's where the origin now is. And then you're clicking on different objects and saying where you want to place them. At this time, once again notice, we don't know how big the object is, how wide the object is. We just picked up a bunch of objects of roughly the capability of the robot to open up fully and grasp those, right? But at this point, we don't know that object is 4 centimeters wide or 6 centimeters wide, any of that, right? Nonetheless, at that bare minimum level, we are able to do the interaction and move around these objects. Squares, blocks, balls, so on and so forth. Okay, so now, how can we also tell the robot manipulator to grasp an unknown object while telling what might be the size of that object and in what pose do I want to grasp that object? Do I want to go to the object and grasp it like this, or like this, or like that? What is that pose of the grasping that I want? And then I also want to be able to distinguish between objects that are going to be grasped coming on top. So horizontal objects, you can just go on top and grasp them. But a tall object like this bottle, I want to go sideways and grasp it at a certain height. So I want to be able to tell what is the height of that object. We will do all of that. So what do we need? There are, I think, some graphics that are not showing up. I need to be able to figure out where is the end effector going to go to pick up something, what will be the orientation, and what will be the grasp spread, how wide, right? I'm going to get that information by using some AR elements to estimate the physical location of the object. We will use some AR elements to figure out the orientation in which we want to grasp the object, and then we will also play with an AR element to figure out the size of the object. Okay? So hence we will get our virtual position, virtual object orientation, virtual object scale, all of which is communicating information about the physical world. So there it is. Same robot, markerless and marker-based approaches along with some virtual interaction. We will figure out all the information. So you see that object is being made taller. That purple element. Same thing again. You see now we are changing the orientation of the virtual element. So the AR element, by playing with that, you are able to communicate a lot of information. Horizontal grasp versus vertical grasp. The default orientation is aligned with the marker, but you can use a twirling action to change that orientation, and you can get exact sizes also if you want, as shown through the scale over there. So then let's move on to some more interesting things. What if I want my robot, maybe it's a welding robot, to weld along a given path? Or it's a robot that needs to move an object while avoiding a certain obstacle, right? So we can actually communicate the path information using augmented reality and then get the robot to draw through that path. And then finally, for mobile robot, I would not have the video for that yet, you could take a smartphone, walk through an environment to create a map of how you want the robot to go through that environment. Okay? So maybe I'm lazy, I don't want to go to 5 different places in my home to pick up stuff. I pick up my smartphone and walk through the home to get to those 5 different places and teach my robot how to do that using the smartphone. Then I'm going to drop the smartphone on this robot and say go to task 1, task 2, task 3 or whatever, and the robot would do that. So let me quickly show you the video for tool teaching. So you can tell whether you are using a pen holder robot or a gripper robot. You can tell where the origin of the marker is when you are doing the training. Okay? And you can do this training without even having a robot close by. Okay? So now we are teaching all these different points through which you would like the actual robot to go to. We will also do the entire simulation before we do the actual experimental implementation. So now that's a virtual end effector. So that's going through the entire path, right? You can also simulate the whole thing in MATLAB. And now you do an experiment with the real robot. So we are teaching this pentagon shape. Okay. The animation is showing that you could actually do that. And then you send the command to the real robot to do the pentagon. So we do a lot of user studies. We have the users come in, take a look at these applications, try them out, and they would tell us whether they were able to do the thing accurately or not, if they felt a lot of cognitive load or physical load. Because if our claim is that these devices provide a highly natural and intuitive way of interacting with robots, well, then the users have to be able to confirm that, right? So we actually do a lot of these kinds of studies and statistically show that this is actually true. Now let's apply the convergence between robotics and AI, for example, for robot hand. Okay, if somebody needs, let's say, they are an amputee and they need a robot hand, we don't want them to have a body-controlled robot hand, but rather this is going to be controlled using their own myo signals. So this individual is wearing this band called myo armband. Around this band there are 8 myo sensors, so they are measuring the muscle signals, and those muscle signals are plotted for all the 8 sensors over here, while the user makes these different gestures A through F. Okay? And as those gestures are made, they are also partitioned here for different faces that the signal corresponds to gesture A, B, C, D, E, F. So we take this data and we take a portion of that data and call it the training data. Okay? And we use that training data to train various machine learning algorithms. And then the data that was not used for training, we test the machine learning algorithm from that data. We also take the data and we filter it out using something known as Gaussian filter, and then do the training again. And we show that for various machine learning algorithms, if you did not do the filtering, this is the best training performance you get, testing performance you get, and this is better when you do the filtering. Okay? So basically, K and N, the K nearest neighbor, ends up performing the best in terms of the performance. But then we also apply that experimentally, where the student is making different gestures, and the robot prosthesis that is put there is actually following, right? This is for stroke rehabilitation. Our colleagues at Langone, they make use of this $10,000 post-op sensor to measure grasping and lift forces for people when they have stroke and they want to do the rehabilitation for them. Okay? So in their research lab, they use a $10,000 device to come up with protocols for doing the rehabilitation, which is good to write your papers, but then how do you get a $10,000 device in every rehabilitation clinic? Or better yet, can you give the device to the patients to use it at their own homes? Right? Because a lot of people don't want to keep going back to the hospital or to the clinic to do the rehabilitation. Okay? So instead, what we did is we designed this device using mechatronic principles, using off-the-shelf sensors, 3D printing, Arduino-like microcontrollers, and then we also interface it with a game, as shown here, so that people can basically do the same kind of training if they want at their home or at the hospital. And now we are actually making use of that device in a clinical study for patients with multiple sclerosis. Okay? In multiple sclerosis, people have a lot of muscle weakness, so they cannot do a lot of the physical tasks. And the idea is if you give these patients a rehabilitation activity, and then in the muscle group corresponding to the rehabilitation activity, if you provide some transcranial direct stimulation in the brain, maybe their learning is better than if you did not provide that stimulation to them. So at this point we have, I think, 7 or 8 of these devices that are in this briefcase-like setup, that patients come to the clinic, learn how to use it, then they take it back to their home. And now they start using it themselves, while the data is being accessed through a cloud system. And what we have just found in a paper that is submitted is that the adherence to the therapy protocol is almost 98%. Okay? So most people are actually sticking to their therapy even though they are not at the hospital or at the clinic. Okay? Adherence of therapy is a very big problem when you try to push it off from the clinic to the patient's homes. But all of those devices were kind of made up, right? I mean, this is not something that you work with every day at your home. This is not something that you need to use for an activity of daily living. But a stroke patient, if they're not able to drink from a glass, right, that's an activity of daily living. Can we make use of such kinds of devices to provide them some rehabilitation training? So here, in fact, that's what we are doing. We have this little glass that has a lot of features on it so that we can make use of computer vision to identify the pose of this glass and the height of this glass. There is also an embedded sensor so we can identify the grasping force being applied. And then a patient will sit in front of the laptop grasping this glass, undergoing the drinking motion, while in this video game-like device, certain activities will take place as they are making the motions, and they will achieve certain score, identifying whether they are doing well or they need to make more progress, so on and so forth. So they are lifting the cup. In the animation, the real, some cooking thing is being lifted, mixed, so on and so forth. Right? Now another ingredient is being lifted. This one is for turning. And then lastly, now we are making the extension where instead of simply doing the drinking action, you could do something with the eating utensils also. So if you have a difficulty after stroke making use of one of your hands, so you can't eat by yourself, we create a game, and in that game, these are utensils with embedded sensors that are doing the measurement of the motion along with the camera, and in the game, you're collecting the score as you're going through the activity. So first we talked about the hand rehabilitation, but what about the entire arm? So if somebody is not able to use their entire arm, can we provide them some way of rehabilitating that so that they can get the range of motion? So for that, we have developed a sensor system we call VICE, Variable Inertial Sensor for Excel games. A person could put 2 of those sensors on each one of their arms and a 5th sensor on their back to create a reference frame. And then through a Unity game, their sensor measurements would drive what their avatar is doing in the game, while the instructor is also providing them instruction. The instruction motion is pre-recorded when the instructor rears the same sensors and creates the motion, but then for the patient, those same motions are to be replicated. So we had a lot of fundamental research to do the experimental validation. We make use of something called a goniometer, which has known rotational motion to determine the corresponding motion of the inertial sensors. There are 4 inertial sensors lined up on this goniometer. We show using the data collection that indeed everything is okay, and making use of what is known as the joint coordinate framework, we are able to get anatomically correct measurements that therapists will be able to understand and make use of. And then we also did a study where we looked at the measurements using our device versus Kinect. Unfortunately, Kinect does not give you the measurements in every angle or every direction because of some occlusion of the sensor, but we show that largely there is not a lot of difference between the Kinect and the IMU measurement, no matter how you look at it. But even that device is too much for certain other applications. So we worked with our colleagues from the nursing school that came to us with a request that they wanted a very low-cost, simple device for their female patients. After breast cancer, often women will have lymphedema, where there may be swelling on the arms, and they have a very specific set of exercises that they need the patient to perform. And when they come to the clinic or the nursing lab, they do that in the presence of these physicians there. So what if they are at home and you want to make sure that they are able to do these activities? There is no way right now to do the therapy compliance. So what we did is, we built this little device, shown right there. So this is, you can think of it as a flower with 8 petals, right? This flower is made of conductive clothing. And then that little black dot, that is like a pendulum that moves around with gravity. So if I move my arm up and down, that pendulum is moving up and down and closing a circuit with different petals, using which I can figure out at what angle did the patient move. So in this particular activity, the patient is asked to move the arm. I guess for some reason this video is not playing. Oh, there it is. They are asked to move their arm 10 times, okay? And by looking at these peaks and counting those peaks, you can easily tell that indeed the person moved his or her arm 10 times, using just that little variable sensor. Okay. So last year, maybe just around this time, late October, early November, there was this little article in New York Times where they talk about the fact that the AI systems that we have today, they are not able to understand abstract information in the way that humans are able to understand that abstract information. How do I mean that? When you drive, you are not constantly looking that there is a car 10 degrees to my right, 5 feet ahead of me. Or there is a car right in front of me, 8 feet ahead. Right? We don't have that crisp information when we are doing the driving. Abstractly, we know that there is a car that entered my right to my lane. I see that they're blinking their lights. They may be coming in to my lane. At some point, they started blinking their left turn light again. Maybe they're going to be departing from my lane, right? So by looking at this abstract visual information, not crisp, measured information, as humans, we are able to do the driving. But today, the self-driving cars, what do? They dump a bunch of sensors on them. LiDAR, this and that, and measure exactly the distance. And now you can't get that distance because it is raining, or the sensor got dirty, or what have you, right? So what if we made use of this abstract notion of understanding the scene and making decision accordingly? So in fact, we had one of my postdocs go around collecting the data while driving around. On the top is the data for a highway scene where cars are coming in, going out from the lane, and then the bottom one is data from residential driving. So all you're doing is you have a camera sitting on the dashboard collecting a whole bunch of visual information, then you sit down and label that visual information. This is supervised training. Okay? So we are training a supervised convolutional neural network with data that is hand labeled. Part of the data is being used for training, the other part of it is being used for testing. And what we showed for this convolutional neural network is whether it is the highway scene or residential scene, we are able to get well over 94% of accuracy in terms of clearly identifying what the scene contained. This is all done offline, after the fact that you have collected the data. It has not yet been used for online testing or for online driving for that matter. Let me skip this. Let's move on to this guy. So now we're going to look at the convergence between robotics and blockchain. Okay? So what is blockchain? Blockchain is basically a way for you to do contract negotiations between parties that don't necessarily trust one another, right? So I don't trust somebody who's selling me something, they don't trust me, so what do? We usually go to a lawyer, we pay the lawyer a lot of money, and then we do our transaction. But that costs a lot of money. So the premise of blockchain is to allow parties that don't trust one another to be able to engage in these negotiations while guaranteeing that the data is not going to be corrupted or massaged for that matter. So here we are going to apply that not for a financial transaction, but rather for information exchanges between robots to be able to identify what is going on. So imagine this room is dark. There is no light here. All of you are individually non-alive robots. So you are all not human beings, you are robots. The lights are off. I am standing outside. I am the supervisor of all the robots, and I want to know where are all my robots and what else is there in the room. There is no camera, no light. All those robots have is LiDAR. LiDAR is a laser sensor that can detect if something is in front of me, and then they are able to communicate with one another on a peer-to-peer network. Okay? So, if I put 10 robots in this room, many objects, robots will see other robots, they will see other objects, but they have no way of knowing what is a robot, what is an object. And the idea is, if I as robot 1 sees robot 2 right in front of me, and I see that this robot is 5 feet away from me, and this robot tells me that yes, I see something 5 feet away from me, then we have confirmed that two of us are robots, robot 1 and robot 2. Now there can be robot duplicate, single duplicate, multi-duplicate, so on and so forth, and you can handle all of that as shown in this paper. So basically we show that you can identify other robots, you can identify obstacles, you can basically generate the graph network of the entire system only by doing peer-to-peer communication and filling out a distributed ledger. Okay? All the robots have their own distributed ledger. They end up reaching a consensus. The only thing we are not doing here, unlike the real blockchain, is we are not doing proof of work, because proof of work would be expensive and we didn't want to waste computational resource, at least yet, on that aspect. So this first piece of work basically allows a bunch of robots in an environment to know where all the assets are and where all the obstacles are. So you might say, so what? Okay. Here is an application where I could have a couple of these robots thrown into this unexplored maze or territory. Each robot is exploring only part of the maze, and when they come in the vicinity of one another, they exchange information through peer-to-peer communication and fill up a distributed ledger. And then that distributed ledger information is used by both the robots to individually stitch up their information to create the entire map. Okay? So now you have a framework where a bunch of robots could be thrown in an unexplored environment to explore pieces and parcels of it individually, but then combine all of that information in a distributed manner without having any central operator. Right? The same framework could be used in problems such as border security, corporate security. You could also use it for smart highway systems, where instead of dumping on every individual self-driving car a whole bunch of sensors, you could have distributed ledgers and peer-to-peer communication so that these cars can exchange with one another not only the state information but also the intent information. We don't only do robotics, mechatronics, and convergence research just as our educational activities or research, but we also try to bring this to local economy. So I've given half a dozen workshops just last year to about 60 New York City companies. These are companies between $10 million to $50 to $100 million annual revenue, and they are all worried about whether they are going to be losing their businesses to the robots. And one way to ensure that you don't lose your business to the robots is by go and co-opt the robots. So some of them have actually started using robots in making food products, small plastic injection molding companies, custom design shops, all kinds of places that are getting into robotics. Suffice it to say that I truly believe that robotics, AI, augmented and virtual reality, and blockchain are going to completely change the world in the next 3 to 5 years. And those of you who have the background in these areas, you would probably continue to be gainfully employed for 10 to 15 years after that, right? Because eventually what will happen is, for the next 10 to 15 years, humans might be creating new AI, and humans might be creating a new AI robot design, but eventually robots will create new robots, AI will create new AI. So then we will have to address the future of jobs. But I'm an engineer, not a social scientist, so I will not take responsibility for that. Are there any questions? Anyone? If this does not make you awake, you should really be worried. You should really be worried. Okay? I hope you take the message very seriously. This is not, simply telling you that jobs are going to go and disappear. There will be jobs. The students who are graduating with mechatronic and robotic backgrounds, they are doing quite well right now. But you have to be prepared for the future. Make sure you also learn some soft skills, human interaction, because those jobs are not going to go away.
No questions?
No questions?
Are you kidding me? Can we set them up? I want to learn right now. I need to hear you.
I'm taking two classes. I've done it like kind of hard. When I used to think about it, there's a lot of I'm also taking materials methods. It's pretty easy. The only drawback is you talk to your on Fridays and it's like almost 3 hours. So,
You just take that, but you can't
but the
Friday.
professor for materials methods is awesome.
I just that gives you practical
Yeah.
knowledge, and I want to add that. Okay. Thank you.
No, I just realized we don't need to hold the door.
Oh, true.
There's no
Go
reason
trick
for
or
us
treat
to do
upstairs.
that.
Oh yeah, I got some like Kit Kat. Like, oh my god. Yeah. Wait,
Thank you for picking up. Have a good day.
you too.
Email who?
Last is ID, so do you want to email him and leave it up front, or leave it in open line?
Left his ID here.
Yeah.
With you?
No,
They just dropped it.
Should we give the public safety his email?
Yeah, I think that's